Okay, everything you say now is recorded.
Okay.
Hi, everybody. We resume our special courses, special edition focused on the big projects out there. And it's a great pleasure to introduce to you Rebecca Bernstein. A brief history, she finished her PhD in 1998 in Caltech. Then she was a Hubble fellow at Carnegie observatories. From 2001 to 2007, she was a professor at the University of Michigan, where we overlapped at the time. And then she went to the sunny California again, 2007, 2014, and she's a full professor, I don't know if it is or was, so it's simultaneous. I don't know, a full professor at the University of California, Santa Cruz, before she joined Carnegie Observatories as staff scientist in 2012. She is currently the project science of the giant Magellan telescope, which has been, people have been talking, the community has been talking in Brazil here and there, and she'll talk about the project today. So without delay, I'll pass the word to Rebecca.
Okay, thank you so much. It's really a pleasure to be here with you today, virtually. Sorry I couldn't be there. I love Brazil. But let me go ahead and share my screen, try to get this going here. Let's see. Okay, can you see that?
Perfect.
Okay. All right. So I am going to give you an update on the Giant Magellan Telescope, an introduction to what the project is, what the telescope looks like, how it performs, and then we'll conclude with the status of the project. And if you know anything about GMT, what you probably know is that it doesn't look like the other two ELTs or like any of the segmented telescopes that are working today, either Keck or GTC. In particular. And by the end of the talk, what I want you to understand is why GMT has its unique design. And I want you to have an appreciation for how that design enables unique capabilities and spectacular performance. So what you see here is my goals for the talk. So specifically, I want you to understand our science goals and the key capabilities that the telescope has that will enable science. Then we're going to get into GMT's key design features, because as scientists, we want to understand. We don't just want to be told how the telescope will perform. So I really want to give you a sense of how the design enables that performance, even compared to JWST and ELT, because I think this telescope really does have some very unique capabilities. And then finally, we'll get into the status of the project and where we are towards building a working observatory. Okay, so I want to start here because in talking about GMT's capabilities, it's really the combination of sensitivity and angular resolution that are so spectacular. And as you'll see, also it's field of view and instrument. So we'll get into all of that. But this is a picture of the Whirlpool Galaxy taken from the ground with Palomar, a 1.5 meter telescope in around the early 90s. And when I hit return, you're going to see the same image taken, the same object taken with HST around the same time, mid-90s. So the revolution brought by HST was not just sensitivity. It's still only a 2.5 meter telescope. The real revolution is in the combination of angular resolution and sensitivity. And in space, of course, the telescope reaches the diffraction limit of the primary mirror, which is 2.5 meters in diameter. And of course, now we have JWST, which is a spectacular success. It's really incredibly exciting. And it being 2.5 times the diameter of HST has 6 times the sensitivity and 2.5 times the resolution, increasing linearly with the diameter of the primary mirror. And of course, it gets to the diffraction limit of that 6.5 meter aperture. So you see here the JWST image compared to the HST. So what will we get with GMT? Well, first of all, you can see this sequence of images showing you what you have from the ground, Same field with HST at 0.2 arc second, JWST at 0.07 arc seconds, and GMT at 0.01 arc seconds, the diffraction limit of the 25-meter telescope. So you get an angular resolution that's 10 times better than HST. You get more than 4 times better than JWST, even at the wavelengths where JWST is designed to work. And of course, getting at the shorter wavelength range of JWST, it's limited by its own pixel scale. And GMT will be able to do adaptive optics down to 0.6. So with wavelength, with the angular resolution going not just like 1 over the diameter, but getting smaller and better with wavelength getting smaller, that's really a much larger advantage than just a factor of 4 over the full wavelength range. In terms of sensitivity, you get anything from a 14 to a 200 to a factor of 200 better than the existing 8-meter class telescopes, because of that increase that you gain from concentrating the light into a smaller area. That flux concentration lowers background, lowers confusion. And finally, remember that telescope is just a light bucket. It's the instruments that do the science. So it really matters how the telescope is designed to enable instruments development and enable instruments to be matched and mated to the telescope. So on GMT, we have a very wide field of view, 20 arc minutes. You're going to hear more about that in a minute. We have wide wavelength coverage from the from the UV cutoff at around 0.32 microns up to 15 microns mid-infrared. You're going to see that we have 2 reflections only, primary and secondary mirror, to the large spectrographs, and we have many advantages for adaptive optics. So what does all that do for you in terms of science? Well, it's not an exaggeration to say that GMT will really have capabilities to transform our understanding of the universe across a wide range of fields. And what this shows is cases from the GMT science book, and in fact, images from the GMT science book, organized into Astro 2020's the US decadal surveys, 3 priority science themes. And those include topics ranging from the formation and evolution of stars and planets, including understanding the statistics of habitable worlds and even searching for life beyond our solar system, to fundamental physics and understanding the basic composition of the universe, including dark matter and dark energy, and understanding the physics and chemistry of the first objects and the chemical evolution of stars and galaxies over time, and the formation and coevolution of black holes and galaxies. So these telescopes, and GMT in particular, will have the power to revolutionize astronomy in all these fields. And as most of you know, and as I'll talk about more in a minute, GMT and TMT joined forces to form the US ELTP, US Extremely Large Telescope Project. And we made this science case together to the Decadal Survey on Astronomy and Astrophysics, Astro 2020. And I really can't put it any better than they did in their report when they said that GMT and TMT will address nearly every important science question across all 3 priority science areas, providing important synergistic capabilities that complement those planned for the European ELT. So I don't think I can add anything to that assessment of the power for science, except to point out that we will also really amplify the impact of contemporary observatories. So with the greater sensitivity and spatial resolution, we have the power to get high resolution spectroscopy of very faint sources to understand dynamics and chemistry of those sources. I'll show you more about that in a minute. And our very wide field of view for GMT in particular, combined with high sensitivity spectroscopy, really enables efficient survey science. That is of particular interest, I think, to this group and the surveys that you have going on in Brazil. Okay, so I'm going to give you a very fast introduction to GMT now with this movie. Starting out, let me explain what you're looking at. You're looking at the side of the Las Campanas Peak Summit at the GMT Observatory in Chile. You can see the lodging buildings and a technical support site, and then you're going to see us come up and over the top of the summit. So here we go. You can see in the background here the other telescopes at Las Campanas. You see us zooming in on the summit here with the enclosure and utility support building and the building where the mirror coatings will be redone every few months on one of the segments. You see the telescope appearing, you see the dome opening, see the enclosure rotating. It's a 22-story building with louvers, of course, to allow air flow through the enclosure to equalize the temperature at night and to reduce turbulence. And here you see zooming in on the telescope again with the secondary mirror structure you can see there in yellow and the 7 large primary segments. This is what the summit looks like today. This is the GMTO summit on Las Campanas Peak. At Las Campanas, the GMTO observatory is within the grounds of the Las Campanas Observatory. You see those residence halls, the technical support site, you see the 2 Magellan domes. And this has been a working observatory for over 60 years now, since the mid-60s. The site where you see GMT being built is leased to GMTO Corporation, and we have the same legal standing in Chile that the other working observatories do. It's really a spectacular site, low water vapor in the Atacama Desert, and excellent atmospheric stability, which you can see here. So this is a plot of image quality as a the cumulative image quality statistics against the image quality itself. So you can see that the median seeing is about 0.63, and the best quartile is better than a half an arc second. And that comes from decades of observations in addition to site surveying on this peak. This is a close-up of the summit. Now you can see again, and I can point out little cars here. I can point out the door in the observatory, the base of the enclosure, but it's very hard to give people an impression of what a rotating 22-story building really means. So let me show you in a more familiar setting. This is a 100,000 person stadium, the Rose Bowl. And I think this starts to give you a sense of the scale. The building, as I've said, is 22-story rotating, has to rotate smoothly to protect the telescope and allow good observations during the night. And the telescope itself is 15 stories tall, or about 48 meters. Okay, so this gives you a look inside the enclosure now. You can see the pier that supports the telescope structure and grounds it to bedrock. You see in purple the structure of the telescope supporting the primary mirrors, and the tripod structure here that supports the secondary mirrors. And you see in blue the internal structure of the enclosure. As I've already said, it's an optical to IR telescope, and it's 25 meters edge to edge on those primaries. You get a better view of the primary mirrors themselves here as soon as my computer cooperates and advances the slide. There you go. So it's 25 meters edge to edge from the outer diameter of the primary. This gives you a better view of the primary mirror itself. It's 8.4 meter segments. Those are the largest mirrors ever made and highest quality. The accuracy of the surface is about 10 nanometers, which is 1/1000th of the width of a human hair. And each one weighs about 18 metric tons. And you can see there, I think for a little more visceral sense of the scale of the telescope, you can see JWST's mirror and illustrates that GMT really does have 10 times the collecting area. So now I want to get into some of the key design features that really enable GMT to have its performance. So the first point to realize is that it's an applanated Gregorian telescope, which means that the primary mirror collects the light. The secondary mirror, I'll put my hand in front of my face so you can see it, is also positive, has positive curvature. So it catches the light and focuses it back down. The primary and secondary mirror segments are both segmented. I'll show you a close-up of the secondary in a minute, but they're paired 1-to-1 so that the light comes to one primary, goes to one secondary, and then goes to a focus. It's a very fast beam. It's f8, meaning that when the light comes to the focus, it's at a focal ratio of 1:8. That enables a bunch of things that are illustrated here. So first of all, that optical design enables the wide field of view with exceptional images over the full field of view. So the telescope itself contributes less than 0.3 arc second to the image quality, which is negligible when added in quadrature to the atmosphere. So we really preserve the seeing limit of the site. The fast beam allows you to get a very small focal plane for a telescope this scale. It's 1 millimeter per arc second in the focal plane of the telescope, which being that compact, it allows you to actually build instruments that can access that full field of view. And I'll show you that in a minute. In fact, let me click again and you can get a close-up there. So you see the beam coming from the secondary mirror straight into the instrument bay. The instruments are carried on this cylindrical structure. We call it the Gregorian instrument rotator. So the large spectrographs are down here. The smaller spectrographs are fed with a tertiary mirror that interrupts the beam and reflects the light to one of these stations. But the large spectrographs, so you can see, get the beam straight from the secondary mirror. So there's no fold. That means there's no screwing up of the polarization. That means this is an ideal telescope for high resolution, high sensitivity observations of objects that are polarized, like supernova, LIGO sources, and many others. Also, we can do ground layer adaptive optics over 10 arc minute field of view out of that 20, and that's limited only by the properties of the atmosphere. You'll see how we do that in a minute. So let's get back to how we do adaptive optics, namely with the secondary mirror. So I already mentioned the telescope is doubly segmented. Primary secondaries are used in pairs. And those secondary mirrors are adaptive. You're going to see the close-up of them here. And they're supported by a tripod structure, which I've already pointed out. You can see it a little better here. So let me go back. You see one leg of the tripod here, another leg here, another leg there. That's really important because one of the things, and I'll point out exactly why in a minute. But let's first just focus on the adaptive secondaries themselves. So first of all, because it's the secondary mirrors that are adaptive, not a post-focal system, meaning basically an instrument that comes after the focal plane of the telescope, because the AO system is built right into the telescope, we get full-time adaptive optics. We can get to any instrument over the full wavelength range that the telescope can see and that the atmosphere will cooperate with. So that's from about 0.6 microns, or in the red, all the way into the mid-infrared. We also, if I told you that we are able to do 50 nanometer position control of these 18-ton primary mirrors, you should laugh at me. There's no way we can do that. What we do, though, is we position the primary mirrors to about a micron accuracy, and then we do the fine positioning with these 1 meter, very lightweight, very agile segments. So these are actually smaller, more agile, more positionable segments than the 1.4 meter segments that are in KEK and ELT. So it's we have a very advantageous system for alignment and phasing. Another key point is that because the telescope is Gregorian, the light actually comes to a focus before it hits the secondary mirrors. Now that focus is extremely important for calibration of the adaptive secondaries, and that's a step that has to be done regularly, calibrating and making sure the secondary mirrors are focused for AO. And so that makes the system very efficient, which is another big advantage for adaptive optics. And finally, not just in terms of operational efficiency, but in terms of light reflection efficiency, because there are only 2 reflections to the focal plane for ground layer adaptive optics, or just that primary, secondary, and a fold mirror for adaptive optics, for infrared adaptive optics and diffraction limited performance, we have very high efficiency and very low thermal background. And you can imagine, example, by comparison with ELT, which has 5 reflections to the primary mirror, to the instrument ports, that leads to a lot more thermal background. Okay, I was mentioning the importance of this tripod structure. So what you see here is that the tripod falls entirely within, the shadow of that tripod falls entirely within the the gaps of the primary mirror. So we have very little diffraction and thermal emission coming into the pupil. So that allows for a very clean pupil. Also, the large segments themselves are very easy to baffle. So if you think about that compared to the smaller segments of Keck or GTC or TMT or ELT, you have miles of edges around those primary mirror segments. And all of those scatter light, produce thermal emission, and they can't be baffled out. So this is a very, very clean, very easy to baffle pupil for high performance in the infrared and for adaptive optics. Okay, so with that, let me just show you the range of performance that GMT will get. So first of all, I already said GMT gets a 20 arc-minute field of view. This is what a 20 arc-minute field of view is compared to the 30 arc-minute moon. So it's really spectacular for even an 8-meter class telescope, but really spectacular for an ELT. And you can see TMT and ELT are able to get about 10 arc-minute diameter or less, similar to that size there is what they're planning for. That's the limit of what ELT can see, and it's the instruments that are planned for TMT. So showing you that wide field performance on a very familiar image. This is the Hubble Ultra Deep Field, actually viewed from the ground. We get 20 arc-minute field of view with a resolution of about 0.6 arc-second median. That's the median seeing at last component. And if we zoom in, you see an example of the field of view and the image quality that you can get over that smaller field of view with ground layer adaptive optics. Now, this is a little counterintuitive, but I just want to really drive home the fact that where that is most important is for spectroscopy of faint objects. So when you're doing spectroscopy, you have the slit matched to the seeing median, so that you can get the resolution of the spectrograph that you're expecting. Remember, the slit, if the slit were wider to admit more light, it would compromise the spectral resolution. So when I hit return again, what you're going to see is how much more light gets into the slit with better image quality. So if this is 0.6 arc-second image quality, this shows you 0.5 or better arc-second image quality. That amounts to 50% to a factor of 2 more light getting into the slits, which is 1.5 to 2 times better sensitivity, which is like building a 1.5 to 2 times bigger telescope. It also allows you to get 30% higher spectral resolution if you instead want to prioritize that for slightly brighter objects and get to the smaller spectral resolution. So it's really very powerful. Ground layer adaptive optics gives you a huge boost for wide field spectroscopy of multiple objects at once. So one of our priority science areas, of course, is understanding the formation and evolution of galaxies. And we don't have to look at an HST field anymore. Now we can look at JWST, and that's really incredible success that JWST is already having in finding the highest redshift galaxies. So this one is at about 30 million years after the Big Bang. And if we want to understand how these objects really formed, we need to do follow-up with very high resolution, high sensitivity telescopes. Exactly the same way Keck and the 8-meter class telescopes were able to get the full science out of the HST detections, sources that were found with HST. And I want to make a point here. You might wonder how the field of view is so important for this, because obviously to follow up an object like this, you're going to use, at the very highest redshift, you're going to use integral field units and adaptive optics. That's the diffraction limit. But for those more intermediate sources that are maybe a little brighter or even just below a redshift of 5, you're going to want that combination of multiplexing over a wide field of view. So this shows you the survey field for the JWST deepest exposures. And this shows you GMT's field of view laid on top of that. So, you know, the ability to get wide field of view, very efficient multiplexing with a very high sensitivity, high collecting area telescope, even 1.5 times bigger than just than the sensitivity that would be implied by the seeing limit, you can really realize how powerful that is. And of course, you don't have to think about just JWST. Projects like Esta, JPAS, LSST, these are all going to need multiplexing to follow up the most interesting, faintest sources to get the chemical abundance and internal kinematics to get the most science that you can out of those surveys. And just to drive that home a little bit more, this shows the GMT field of view compared to the JWST survey field, HST survey field, the WFIRST survey field, and some existing telescopes. And again, GMT's focal plane is 1.2. This image corresponds to 1.2 physical meters in the focal plane of GMT, which you can build an instrument to access. TMT, on the other hand, while they are able to form that full field of view, it is a 2.4 meter physical scale at the focal plane of the telescope, which makes it very, very hard to build an instrument to match that field of view. So the largest field of view that TMT is planning has a similar 1 meter collimator optics and allows for a field of view that looks something like that. So this is one of the things which makes the combination of GMT and TMT so powerful for USELT, and it's one of the things which makes GMT really a spectacular complement to the European ELT. And just to drive that home a bit more, what I'm showing here is the 5 sigma limiting magnitude of some surveys that will be contemporaneous with GMT, and the 5 sigma GMT detection limits at a 20-hour integration. So in the optical, the instrument GMAX will get down to here. In the infrared, the instrument GMTIF will get down to this detection limit. And that really shows that essentially you can take a spectrum of anything in these catalogs to do any of the diagnostic science that you see listed over here. All right, so what people really think about when they think about these ELTs is the diffraction limited performance, and that is without a doubt critical. So let's just talk about GMT's AO performance. So I've already mentioned that we'll get 10 to 15 times better than HST, and that's by pushing into the shortest wavelengths. We get that extra boost from lambda. And by pushing again into those shortest wavelengths, we get 4 times better than JWT, or even better. In terms of sensitivity, I already mentioned that factor of anywhere between 14 and 100 because of that extra boost that comes from focusing light and reducing background confusion and background flux contributing to the sources. So our NGAO performance will get to the diffraction limit over the full 0.6 to 2.5 micron wavelength range. And the reason we can do that is because of the very high actuator density of our adaptive secondaries, which are matched to the atmospheric turbulence scale that really lets you get down to these shortest wavelengths. Our K-band STREL, which is where everybody characterizes STREL, so that's what I'm telling you as well, is 80%, which is extremely high compared to the 8 meter class telescopes, and it's the same spec as for TMT and ELT. Our astrometric accuracy is 0.01 milli-arcsecond RMS performance in a long exposure. And you can see JWST and GMT again compared here. Of course, we will also have laser tomography adaptive optics using 6 lasers and combining that information from the 6 lasers tomographically to get the best possible correction over a wider field of view than you can get with just NGAO. So we'll get to a slightly higher image quality, still the diffraction limit, but then letting you get to that large field of view so that you can study larger objects, not just the smallest objects. So letting you get good images over galaxy scales at say cosmic noon. The image quality will be more than 50% STREL, and we'll be able to get to more than 80% of the sky. And what's being shown here is the current state of the art at the galactic center using a VLT system. This shows you, when I hit return, if it will cooperate, shows you what you'll get with GMT. And like I said, more than 80% of the sky can be observed with this system. So just a very quick example of some of the priority science. On the left, you see the example of direct imaging of exoplanets in reflected light. And this lets you see into at distances as close into the central star as the habitable zone of stars, out to 100 parsecs. What you're seeing here is a coronagraphic image taken with the GPI instrument. It's the current detection limit. And you see a detected planet there. This is made a pick, I believe. And this shows you what you can get with GMT. So you could see that same 10 Jupiter mass planet easily detected, and you could see much fainter planets detected much closer in, getting to a separation of 3 lambda over d, or about 20 to 30 milliarc seconds. I'm going to show you that we have an instrument that's planned to push down into doing this at the shortest wavelength range, 0.6 microns, which will allow us to get to even smaller separations because of that lambda in the numerator. Over here, you see the resolving power of, for galaxies at cosmic noon. So this shows the star forming, illustrates that we'll be able to detect star forming regions at 60 parsecs at a redshift of 2.5. So just to give you a quick sense of what some of the limiting detections are at for a range of different science cases. In the solar system, we'll be able to detect a 30-kilometer feature on Jupiter. I already mentioned the habitable zone detections, star clusters, for example, at 1 parsec diameter at the Virgo cluster. And then this is the example of cosmic noon. So just to, again, give you a little better sense of what that means for science, this shows a simulation of observations. This is a simulated observation. The simulation comes from the fire simulation. This shows a galaxy at a redshift of 8 when the universe was 5% of its current age, or about 600 million years after the Big Bang. This is what you can see with a 30-hour observation with JWST for that target. This shows you what you can get today with Gemini and the NIFS telescope. So a little bit better resolution, but not quite as good sensitivity because JWST is above the atmosphere with less thermal background. This shows you what you'll be able to do with GMT and the light focusing power to really increase the sensitivity. Less than 0.02 milliarc second astrometric stability. And of course, in order to really understand an object like this, you need the spectroscopy to get the internal physics, the kinematics, and the chemistry. This shows the spectrum that you could get from a source like this. You can see the rotation curve essentially there, and you can see the emission line detected spectrum there in even a 1-hour exposure. All right, so now let's talk about the scientific instruments, emphasizing again that it's the instruments that allow you to do the science. So this shows our gravity invariant station in green, which is where our precision radial velocity instrument will be. As I peel away the layers of the telescope here, you'll see the instruments. First, get my computer to cooperate. You can see the smaller instruments on the top platform behind the primary mirrors. And you see our small single object spectrographs, the infrared shell, an infrared integral field spectrograph, and high contrast AO imager. I'll show you more about all of those in a minute. And then below those, in the body of the instrument mounting system, is our big commissioning camera, a wide field optical spectrograph, and a fiber feeding system, which can feed our optical spectrograph, GMAX, or in the future, our infrared wide field instrument. So this just gives you a better sense of what those instruments are. I'm going to go through this very quickly, and since this will be on YouTube, you can go back and look at it again if you're interested. But our shell goes over the full wavelength range of the optical. It gets up to the very highest resolution for precision radial velocity, can be fed with natural seeing or GLAO, or fed by manifest. And in the future, fed by our extreme AO instrument, which will allow it to do really spectacular work for studying exoplanets and their atmospheres. The precision radial velocity performance is listed here. And this instrument I want to emphasize is in construction. And we expect it to be used in the next few years on Magellan prior to being commissioned on the GMT. You can see some of the science cases here, and you can see the PI in the corner. The same format will be on the next few slides. So I'll just calling out some points I really want to emphasize in orange, and the science case and the PIs. You'll see that repeating. Okay, so here's GMAX, our wide field instrument. I just want to, you can see the spec here again, full optical, medium resolution. This one fed by slits for the greatest sensitivity, gets to 7 arc-minute field of view. GLAO fed, of course, and manifestable as you get to that full 20 arc-minute field of view. That's our fiber feeding system. This instrument will have very high throughput, which, remember, it doesn't matter if you get, first of all, you can collect the light with the primary mirror, but then you have to get it to the focal plane of the telescope. Having few reflections helps you with that. And then being able to build very high throughput instruments is the next key, which really allows you to do high sensitivity science. So this instrument is estimated through its optics and the grading to get to between a 45% throughput and a 65% throughput, which is really spectacular for a wide field optical spectrograph, let alone one on an ELT. There's some of the science cases, of course, and this is our GMTIFS instrument, our integral field spectrograph. Again, full JH and K bandpass from 5,000 or 10,000 resolving power. You can get a range of instrumental for spectroscopy fields of view. The widest field of view for direct imaging is 20 arc seconds. Works in both AO limits, and again, very high throughput for an infrared IFU. There it gives you a little bit better view of how the light gets through, how we baffle, and you can see some of the optical system there and there. Let's see if we can advance the slide. This is an infrared shell, which covers in one exposure everything from 1 micron up to the mid-infrared 5 microns. It gets very high spectral resolution. It gets one object at a time through a slit for highest sensitivity. It's completely AO fed, very high spatial resolution, and it uses silicon immersion gratings for very high throughput, allowing you to use a very compact beam and to get to those highest resolutions. And the really spectacular thing about this instrument is it gets that full bandpass in one exposure. So if you think about if you had to chop that exposure up into 20 exposures to get the full spectral range, that reduces the efficiency of the telescope by a factor of 20, for example. If you had to do 100 exposures, reduces the efficiency of the telescope by a factor of 100. So instruments that can be built with this kind of performance efficiency allow the telescope to really do its science. And this one is in preliminary design, but it can't, since it's a single object spectrograph, it can be built to work on Magellan. And again, we will get it onto Magellan doing science in the next few years, well before GMT is in operation, to work out the kinks and let us do some advanced science with this. Commissioning camera is just a straightforward, full optical wavelength imaging camera that's going to be used for commissioning. It get the various high spatial resolutions delivered by ground layer adaptive optics. And this is the camera that will allow us to do polarization imaging with no folds in the beam. So remember, when you have a 45-degree fold, you select out one polarization mode. We're not going to cut the efficiency that way. So this instrument's fed just from the secondary mirror. And that, again, is a huge advantage for science that can't be done with TMT or ELT. Here's our manifest instrument. I just want to call attention to the starbugs, which position themselves using little piezoelectric suction system, a little vacuum system that allows the starbugs to self-position and move across the focal plane. There's a test bed system, or really a demonstrator called Taipan that's already working on the UK Schmidt telescope at Siding Springs. This will allow us to multiplex the efficiency of the instruments between 10 and a factor of 100. Okay, this is GMAG AOX. So this is an extreme high contrast imager. So this is for really imaging of exoplanets. The spectacular thing about this instrument is that the design is built on deformable mirrors using a sort of a deformable mirrors internal to the instrument that sort of work with the telescope like a whooper and tweeter to get to a real boost in relative sensitivity, contrast levels, and very, very allow you to work very close into the central star. So this design is being used for GMT-AO's test bedding system to really let us demonstrate how GMT will do its adaptive optics. This instrument can feed GCLEF and GMT NIRS in the, with a fiber to allow not just imaging, but spectroscopy of the planet once it's resolved. And it builds on the GMAG-AOX design, MAG-AOX design, which is an instrument that's working today and for several years now on the Magellan telescope. And I just can't resist showing you this image taken with MAG-AOX at H alpha. So this shows the ability to get to spectacular diffraction limit in the optical. They're working now at 3 lambda over D. They're working on the AO control, wavefront control system and strategies to allow you get to even closer inner separations. And this instrument is now in preliminary design. Again, with the return, there we go. Okay, so I just want to, actually, just in the interest of time, I'm going to skip this. But if you're interested, you can ask me questions later about how these instruments compare with the ELT system. I'd be happy to come back to that. All right, so let's get to how the status of the observatory and where we are today. So you can see from this close-up of the summit that we are well into construction. The hard rock excavation for the pier and for the telescope foundation is done. You see the foundation of the outer ring wall has been dug here. This is where the pier of the telescope will go to connect the telescope to bedrock. And you can see a utility tunnel that will go to the utilities building off to the side to keep that heat and vibration away from the telescope. You can see the design of the enclosure here. The final design will be complete within the next year. The design of the telescope incorporates CFD modeling and wind and water tunnel testing that includes both the enclosure and the site topology and site survey data to really allow us to design the dome to best control the airflow through the dome and prevent internal turbulence within the dome. That work was done by GMT's internal integrated modeling team and also with contributions from Boeing Corporation. So I like to joke that if you don't believe our modeling work on the design of the dome, you really should not be getting on airplanes. So we're confident in it. You can see the windscreen here. You can see the telescope structure here. It's reaching its final design just within the next few months. You can see some interesting features. You can see the azimuth bearing here in light blue and blue. That's the disc on which the telescope rotates. You can see the C-rings here that allow the telescope to nod in altitude, and the azimuth hydrostatic bearing pads right there. You can see the primary mirror covers that keep the mirrors clean. That's important for throughput and keeping high efficiency of the telescope. And you can see where our telescope will be fabricated in Illinois at a company called Ingersoll Machine Tools. So they actually built us an entire new facility, a new building for doing the machining and test assemblies. You can see the essentially test pier here where the telescope will do some partial assemblies. And you can see a close-up of that here. You see that ring wall essentially mimicking the pier. And you can see how huge that bay is for the test assembly. You can see prototype testing underway of the hydrostatic bearing pads right there. And you can see the prototyping for the Gregorian instrument rotator. So carrying those instruments in the middle of the telescope body, we want to make sure that that bearing is really up to performing for the life of the telescope. You see our adaptive secondary mirror. It's in final design. The final design was complete several years ago now, and it's the first off-axis segment, complete segment is now being built. You can see an exploded view of the components of that off-axis segment from the the 1 millimeter thick surface mirror that actually is able to articulate to correct the turbulence in the atmosphere. And I want to just draw your attention to the 0-dir reference body. So if you're going to move that mirror very accurately, you need something against which to push, for the actuators to push. And this shows the 0-dir reference body being machined in the shop. So that will be, that fabrication is underway. This is an example of one of our gorgeous mirrors. So this is a little confusing what you're looking at here. So let me just explain. These mirrors are light-weighted, which means they have a honeycomb structure behind them. So most of the, so there you have about a 5 or 6 inch thick surface at the top. And then the rest of the depth of the mirror, which is quite thick, is actually all honeycomb structure. So remember, the glass is structural in this case. The mirror is just the thin aluminized coating on the top. So what you're looking at is the polished glass. And where you see a dark hexagon, that's where you're looking down into the strut, into the solid part of the mirror in between the hollow honeycombs. So the honeycombs are, you're looking at an air glass surface where the glass is frosted, so it looks white when you're looking through it. So what you're seeing here is the surface of the mirror, the ribs in that honeycomb, and the honeycomb cutouts themselves. So as I already mentioned, these are about 18 metric tons each, or about 35,000 pounds. Segments 1 and 2 are complete. These are being made at the University of Arizona Karas Mirror Lab and underneath the football stadium, in fact. Our third segment is in acceptance testing now. You see it here on the polishing jig, but it's in acceptance testing. The polishing is complete. Segments 4, 5, and 6 are all cast and they're waiting to be polished. They had to build this stand to house our mirrors. They're backing up in the mirror lab there. And segments 7 and 8 are still to be cast, and we'll do segment 7 later this year. You can see the structure of the mirror cell that supports those mirrors. So remember, these are very heavy mirrors, and they need to be able to work and hold their shape very accurately when they're pointing around the sky. So they go to high, 60 degrees over means your very heavy mirror is being supported this way. So to keep them from flexing under their own weight, under different gravity loads, they have a very complex support structure. You see actuators, you see the whole actuator and thermal control system here. And this shows you what the first test cell looks like already assembled. It passed its test in the mirror lab at University of Arizona with flying colors. Okay, so the partnership. This shows you where our partners are located around the sky. Of course, Sao Paulo here. There's I think 8 universities and research institutions in the United States. We also have the Korean Astronomical and Space Science Institute, 2 institutions in Australia, which together represent the entire Australian community. And we've recently been joined by the Weizmann Institute of Science in Israel. So we are a collection of research institutions and universities. And recently, as I mentioned before, we have joined forces with PMT and Noir Lab, which is a private, essentially a private company that has formed and is contracted by the National Science Foundation to represent the universities that do research in astronomy. So Noir Lab is part of AURA, which is the Association of Universities for Research in Astronomy in the United States. So we've joined forces with these 2 partners to produce a world-leading OIR system that has not just the revolutionary capabilities for science, sensitivity, resolution, and those state-of-the-art instruments that I've been pounding for the whole talk, but also this will allow us to have the telescopes have a much greater impact. By working together, we get the benefit of 2 telescopes, which I'll talk about in just a second, but we also get much better integration of the community with the telescopes, which, as we've seen from surveys like Sloan, and as we know from the space telescopes, really leverages their impact for science. Also, we'll have better user support for better data reduction, faster publication, and the data pipelines and archives that we'll be able to support will be much more sophisticated with the support of NOIR Lab, which has experience running Gemini and the Space Telescopes. So let's talk about what the two telescope system buys. First of all, a full sky access for the coverage of, for example, fast fading variables, and access to unique sources like planets and the local objects in the local group and the galactic center. Remember, the galactic center is in the south. So that's really, GMT will be the ideal place to do that galactic center science. Powerful instrument suites can be developed with diverse and unique instruments in the first generation. I've really emphasized the incredible array of unique capabilities that GMT will have with first generation instruments. And by having two telescopes, we'll be able to specialize those over time. And finally, just more hours on sky will allow larger programs and also discovery scale projects that are riskier. It will allow and I think this is really important. When you make extraordinary claims, you require extraordinary proof. So having the ability to confirm those extraordinary discoveries of new physics or biosignatures is a real advantage to a bihemispheric system. So just very clearly to let you know where we are with the development of GMT, we are working now to engage the National Science Foundation with a series of preliminary design reviews. That will be the start of a process to get the National Science Foundation on board with both telescopes. We expect the final designs for those, if that work with the National Science Foundation, to take place in 2023. And we anticipate the start of construction funding in earnest. I showed you we have a range of construction going on that's privately funded. We will continue that, but the construction on the summit will continue in earnest when we have the NSF on board. And I'm going to end there with this vision of GMT in operation, and I will take any questions. So thank you very much.
Okay. Thank you, Rebecca. It's amazing presentation.
I'm going to leave my slides up in case anyone wants to go back or look at any other slides, since I have a few in reserve. So I will do that, if that's all right.
Okay. So let's open for questions. We have Simone.
Yeah, so thank you, Rebecca. It was really amazing. I was shocked to know that TMT has two telescopes in the north. I didn't know that.
Sorry, that was confusing. Let me actually go back to that. What this shows is two possible sites. So one site, yes, sorry, I should have said. One possible site is at Mauna Kea. If that does not turn out to be possible, the alternative site is at La Palma. But what this shows is the very similar latitude of those sites, and that you still get a good spread in longitude between GMT and TMT. So it's one or the other, not both. Sorry. TMT having two telescopes would be awesome, wouldn't it?
Yeah, I was wondering why you do need so two.
Thank you. Thank you for providing an opportunity for me to clarify that. I'm sorry.
Okay, that's great. But in any way, having TMT and GMT is really fascinating. You have there will be some amazing facilities for observations, and I think the main message is, especially for stellar astrophysics, is that we have to do science not only different like large surveys like Sloan and so on, but we have to do science in another way, because for example, you have high resolution spectrographs, but you cannot point to one star. It's not a sense of having a fainter star anymore. So it's completely different, right? So it's even different from what you have in Sloan, for example.
Yes,
So,
it's
yeah,
exactly right.
yeah, great. Thank you very much.
Okay, Andres.
Hi, can you hear me?
Yes.
Yes.
Okay. Oh, thank you so much, Rebecca, for your nice talk. It was very amazing. The way you
pleasure.
explained different things. My question is more a general one. And from your point of view, what do you think young people, young researchers, the skills they need to develop or to acquire in order to, well, take advantage of this nice year, this nice time we are living in this technological advance, in especially this GMT telescope, because there will be some projects that are the main focus of observations. So what do you think about that?
That is an excellent question, and I really appreciate you asking it. So in my own experience, there is you can imagine that these telescopes will be used in Q mode. So in order to make the best use of all of the time that's available and match the project to the seeing and atmospheric conditions on an hourly basis, it will be necessary to schedule them in a dynamic way. And so you might imagine that it's not important to have the skills yourself as an observer to go, and it's not so important to go to the telescope and be able to be an expert observer yourself. And I think that is absolutely untrue. The ability to plan an effective experiment and understand what you can detect and how to take the data to detect it, all of those skills depend on having experience using similar instruments on the existing telescopes. And so I think the best thing you can do as a scientist preparing to use the ELTs is do the precursor science as much as you can, pushing as far as you can with the 8-meter class and smaller telescopes. It's not necessarily important that they be 8-meter class telescopes, but they be similar instruments so that you get the sense of how those instruments are used, how the data is reduced, what is important for being able to reduce the data and get the result you need. So experience at the telescope. I think that's really key. And then I'm sure a theorist would tell me, in order to know what questions to ask, we really need to do the precursor theory and simulation. And that is also true. But I think, a telescope is used by observers. The observers need to have the skills. They can't put that off to anyone else.
Thank you so much.
Go for it.
Before we go to Dinara, there was one question in the chat. I'll read for you. Thanks, Rebecca. Amazing presentation project. Congrats. I'd like to understand better if it will be possible to study TNOs and centaurs with it.
Yes, that is a great question. So we are absolutely planning. Let me go back to the instrument slide. So, not that one, this one. Okay, so one of the requirements for our instruments is that they be able to come on sky in 15 minutes or less. So all of these, we have 10 instrument stations, and all of those instruments will be usable on any given night. So for example, if a LIGO source goes off, and there are four telescopes at Las Campanas that can do the work to identify what galaxy those LIGO sources are in, for example, and tell us quickly where we want to point in the sky, or GMT has a wide field of view, we can also do the direct search for those rare sources after an event ourselves. And we will have a system for targeted opportunity observations and interrupt time so that we don't miss that spectacular science and the spectacular opportunities that come with those sources. But I also want to point out that surveys like LSST will be discovering dozens of supernovae a night. And we can just plan to spend the first hour of the night doing follow-up of those rare sources if it turns out that the sources discovered in the previous night were interesting and unique enough to warrant immediate follow-up. So target of opportunity is going to take on a whole new flavor with LSST. We're going to be able to plan for target of opportunity, but both will be available: rapid acquisition of interesting sources and planned. It's a great question.
Okay, Dinara? Dinara, did I mispronounce the name? You have your hands up.
Hear me?
Yes, we hear you
Yes.
now.
Okay. Hi. Thank you for the presentation, Rebecca. Also, so like I would like to ask, you were talking about the TMT and the two possible sites, and I remember that one of them, I think it was the original like idea for the site, and they didn't build it there. I mean, at least not now. Yes, exactly, Mauna Kea, because there were protests, right? Protests
Yes.
because it was like sacred or something like that.
Yes.
And I was wondering both on the cultural impact and also the environmental impact on this kind of projects, because they are so big. You show the GMT and it's like so big. Do you have any kind of study on the environmental impact, or do you know any kind of impact, like do people
Yes, I
you know,
understand
like
what you're
complain?
asking. Yeah, absolutely. So let me show the site again. So this is the observatory at Las Campanas. So the whole, there's a fairly large area, I think it's like 50 square miles, are owned by the Carnegie Observatories, which is one of our partners. And they have been operating a telescope there for these telescopes. So the Magellan telescopes, and over here you see even smaller telescopes. The first telescopes that were built there were a 100-inch and a 40-inch telescope over off on this peak over here. Just in the 2000s, the Magellan telescopes came online. And GMT, as I already mentioned, has the summit. We did an environmental impact study, but as you can imagine, the environmental impact is very minimal relative to what's already at the site and is already in operation and is already having minimal impact. But we work very closely with the Chilean community. We do a lot of outreach, we do a lot of education work, and the vast majority of the people who work at the site are Chilean. And we work very hard to make sure that our engagement with the Chilean community is very positive, it's very mutually supportive. And, you know, I think the culture in Chile is one of enormous pride in astronomy. So I think we have very good relationships there, which we work very hard to maintain and to really make sure that they're mutually beneficial with the Chilean, not only people, but the Chilean astronomical community as well. So the Chilean community is will have 10% of the telescope time, as they do for all observatories that are operating in Chile. And they're part of our science advisory committee. So we feel a very close connection to the Chilean community, and we will certainly continue to work very hard to make sure it's beneficial.
Okay, thank you. It was a nice answer.
Okay. Any more questions? So Rebecca had one I was wondering if you could elaborate a little bit, because you mentioned this joining or partnership with TMT. And I was wondering, and I'm sure that many people, some people, at least some people in the audience will be interested in knowing is the partnership versus access to the data, or if there's some kind of geo program.
Yeah, that's a great question. So the two observatories are independent in the sense that we're building GMT, they're building TMT, but what we're trying to do is make a common user interface so that it's easier to use both telescopes, so that people can essentially, when they're looking at one or the other, see you're not looking at one or the other, you're looking at the suite of instruments and the suite of capabilities together to more effectively plan science. Our partners then would be our partnership, who you see here, and the National Science Foundation. So through the National Science Foundation, the whole US community would have access to whatever fraction of the time the NSF supports. And our partners, our other independent individual institutions and universities, would have access to their fraction of time. Just the same way, so the NSF and the community just come in as any of these partners do, with access to their fraction of the time. Same would be true for TMT. And then the time allocation goes on within the individual partners and within the NSF, sort of the way it does for Gemini. And I think there would be a proprietary time of the usual sorts of 12 to 18 months, so that people can get their science done. That's exactly the way it is on space telescopes now. So you've got a proprietary period to get the science done that you're proposed for, but then there would also be then access to the data archive to the whole community, to any of the partners who are within this partnership. So in the same way as Australia Astronomy Limited makes the Australian community have access to the telescope, the National Science Foundation would make our community. It's exactly the same as Australia Astronomy Limited versus ANU. So that's a university, this is the rest of their community. We have these universities and then the rest of our community, just coming in as the standard, just behaving as standard partners. So we are adding new partners all the time. We're talking with other universities that are considering joining GMT, and we would more than welcome new partners, international partners as well. Those partners would have access to a fraction of their time guaranteed. They'd have then their proprietary time, access to the data, and then they would have access to the archive. So it really leverages everyone's ability to do science. It leverages the community engagement, and the way we understand the time allocation through the National Science Foundation, it would be for both, I think that I have it here, both for very large projects. So for example, with HST, you had key science projects. So we imagine that there would be very large projects for which lots of time is required. And the whole community of GMT would be welcome to join those, so that you can sort of leverage the efficiency of doing those large surveys and large scale projects. And then the community would also allow everyone, through NSF time, through the partners time, standard PI individual scale projects. So it would be, I think, if you picture in your head a lot of what goes on with HST, both the key projects and the individual investigator projects. Does that make sense?
Because you mentioned the LSST and the TMT and GMT, how are they, of course, getting a precise time for these projects it's extremely difficult, but they are in different time scales.
Yes, that's a good point. So we expect first light with GMT and TMT. Well, for GMT, we expect first light around early 2030s. So 2030, 2031, something like that, if we stay on the current expected track. So LSST is right now delayed a bit, so it won't, it'll be starting sometime in the mid 2020s. So there will be a time delay, but by then, the archive will be there, and we expect to be able to do follow-up of those sources.
Okay.
Yeah, it's a good point.
Okay,
It won't be
perfect.
entirely
Thank you.
contemporaneous with LSST. There's definitely a time lag.
Okay. All right. So I don't see any more questions from the Zoom. Simone, are there any questions from the YouTube? Because I'm not following that.
Okay, great.
No questions there.
All right. Okay, Rebecca, thank you so much for
My pleasure.
coming under the conditions.
My pleasure. It's really nice to talk with you guys.
It was
I'm
fantastic.
glad Zoom allows this. It's one of the nice things about the way we've evolved during the pandemic.
Yeah.
Right.
All right. Thanks
Thank
again.
you very much.
Okay. Thank you so
Bye-bye.
much.